Green's theorem. Let D be an open, simply connected region with boundary curve that is piecewise smooth, simple closed curve oriented counterclockwise. So let's stop there for a minute and just talk about all of those components of Green's theorem, the initial conditions. So let's start with open. So open simply means it contains all of its interior points. Simply connected region means that my region cannot have any holes, because the definition of simply connected region means if I draw a closed curve in there, it has to be able to sink down to a point and stay in that region. But if I had a hole, notice this, I can only get so small before to stay in the region, and then I have to stop. So a hole does not permit me to use Green's theorem. But we will talk in later videos about a workaround of this. But for now, simply connected region simply means I cannot have any holes in my region. Piecewise smooth. So when we look at this curve here, it has to be piecewise smooth. That simply means that for the most part, it's going to be smooth. Next one. Simple closed curve. So that means it starts where it ends. That means it's closed. And also, the simple part means it can't cross itself. For if it does, we can't use it. We can't use Green's theorem. The next one here is oriented counterclockwise. So that means it has to go in a counterclockwise direction. So that's the idea here. So if it's not counterclockwise, I can't use Green's theorem. So let's go on. We got a few more conditions here to use Green's theorem. The next one is, it says let F equal PQ be a vector field with component functions that have continuous partial derivatives on D. So when I look at P and Q here, their partial derivatives first have to exist, and they have to be continuous also. And then, once all those conditions are met, then we can say that the integral of f dot dr equals the integral of p dx q dy, which equals qx minus py dA. Now, the power of this is sometimes I have an RT that's easy to find, and that f dot dr, which is really f dot r prime t, is something easy for me to compute. Okay, but if I don't have that, and I'm going to have to come up with a bunch of RTs to make this happen, the area formula might be much more useful in that capacity. So that is truly the power of this. Now this little circle around here, that little circle you see there on the integral symbol, means closed, simple closed curve, oriented counterclockwise. So when I see that, I'm looking for that counterclockwise direction of that simple closed curve. All right, so let's take a look at this example below now. It says, for the following exercises, evaluate the line integrals by applying Green's theorem. So we're going to take a look at number 149 here. So it gives us this integral here, where C is the boundary of the region lying between the graph of y equals x and y equals square root of x, oriented in a counterclockwise direction. So let's graph those equations, y equals x and y equals square root of x. So there's our graphs. And when I look at this, notice this is the region that we're talking about here, right in there. And what we're going to do is we're going to create this counterclockwise path around it. It's going to go in that direction and that direction. That's what we're actually looking at here. So just something to think about as we go through it. And don't forget, there's a vector field on this graph as well, and I didn't draw it, and I'm not going to. But if we think about what the function or what the vector field is of f, it's given to us in the integral itself, because this is the integral we actually see down here. And if you look at the setup, I have my P here, And this here is my dx. And then I have my q here, and there's my dy. So what we see here is this is my p, and I call it pxy. That's really what it is. And here is my qxy. And that's what our functions of our vector field are going to be. So that's going to be, for f equaling, we're going to get the sine of x, cosine of y, comma, xy plus cosine of x, sine of y. So that's our vector field that we're actually looking at here. And yes, it was hidden right in the integral itself. Now, instead of coming with those RTs as I expressed in the beginning, that would be using the integral of f dot dr. We're going to actually use this one here because it's a lot easier here. So we're going to use the one for the area. So first off, we're going to need qx and py. So my q is my second function of my vector field. And I have to take that derivative with respect to x. So I'm going to write qx here. And that qx is going to be y plus, I should say minus, sine of x, sine of y. And then I'm going to do my py, because that's what the formula calls for. And that py is going to equal, and that means I'm talking about my first function, or first component in my vector field. And that's going to be negative sine of x, sine of y. So now for the double integral here, and I'm just going to leave the d here for now, I'm going to have qx. So my qx is y minus sine of x, sine of y. And it's going to be minus our py, and I'm just going to use a parenthesis here. And then I have the negative sine of x, sine of y. And that's going to be dA. I like to simplify this as much as I can before I think about using the bounds for this, so we can figure out what we're going to do. All right, so now this is going to equal, because I'm going to clean this up a little more. There's my d there. And this is really going to be a plus there. So those are going to cancel out, and I'm just going to be left with y dA. Now for dA, so remember, we're talking about this region in here. So if I think about my double integral now, my double integral here, I can see that if I do my dy first, I'll put the y in there, and I say my dy because I already have these functions y equals some function of x. So then the lower bound then I can see is going to be this line here, which is my y equals x line. So it's going to be x is my lower bound, and my upper bound is going to be the square root of x. Because keep in mind here, the square root function is above the y equals x line. So then for my dx here, I would have to know where this intersection point is at, and it's at 1, 1. And if you're not sure, what you can simply do is you can plug one function into the other. So for instance, if I wanted to do that, I could take this x, square root of x, and plug it in for that y. And then I could solve, and I would get 1. And then find the 1 for the other letter. So that's how that would work. So anyways, in the process of that, this is what I end up with. So then for my x bounds, that's going to be from 0 here to, oops, went too far, to 1. So it's going to be from 0 to 1. So that's the nice thing about this. I don't have to go through two RTs, because that's what I would have to do if I integrated using the f dot dr. So this makes it really nice to work with in that way. So I could just simply use the region. I know upper and lower functions. It makes it very easy to run through this using dA. So my first integral is going to be 1/2 y squared from x to square root of x. and then dx last, which this equals from 0 to 1, and when I plug in the upper bound, I'm going to get 1/2 x, because I'm going to square it. Oh, no. I mean, yes. All right, so that works. So I'm square rooting it because it's dy I just did. And then I'm going to minus the 1/2, and that's going to be x squared. And then I have dx. So now I'm going to do this integral here. So between 0 and 1. So this is going to be 1/4 x squared minus 1/6 x cubed. And you could have pulled the 1/2 out to begin with and not worried about any of that. That probably would have been a little better to do this with. But it's between 0 and 1. So then for our final answer here, I'm going to plug in the 1 in both the x squareds there. And 1 squared and 1 cubed are both 1. So this is going to be 1/4 minus 1/6. And when I plug in 0 in both those, I'm going to end up with a minus, because the lower bound, a 0 there. And then 1/4 minus 1/6. That equals 1/12. So there's our answer for this integral here. And again, it was very nice because I had all the information I needed to use the area instead of the RTs, which is around the boundary there. I would have had to create 2 RTs and then 2 integrals. So this makes it so much nicer, and that's really the power of Green's theorem. Now just remember, with Green's theorem, it only works in 2 dimensions. So that's one of the hang-ups with this, because this is multivariable calculus. We're going to go to 3 dimensions, so we have to use something else, but an extension of these ideas nonetheless. So again, there's our answer.